So in this lecture, look at orthogonal matrices and the principal axes theorem. So these are the two main, I guess, parts to this lecture. And the first two parts are just more, you know, a little bit of revision and refreshing your memory. Okay, so symmetric matrices are square matrices. We're going to look at some particular matrices with only real entries. And a symmetric matrix satisfies this identity. So if you take the transpose of the matrix, then you don't change the matrix at all. Okay, so the transpose is just the original matrix. So when we talk about the transpose of a matrix, all you do is, let's say you have a 2 by 2 matrix here and you want to take the transpose, you just take the first row and make it the first column. Take the second row and make it the second column. Okay? Now a couple of important observations. I'm not going to prove these things, but hopefully you can get a feel for what's going on with the 2 or 3 examples that I've given you. If you look back at every example, each of the eigenvalues were real numbers. There were no complex numbers in there. The corresponding eigenvectors all had real components. Now the eigenvectors associated with distinct or different eigenvalues are orthogonal to each other. And I claimed, okay, and this last bit might not be in your notes, so make sure you have this down properly. I claimed that if I compute, say, 2 eigenvectors and they're not orthogonal, I can actually go back and choose the eigenvectors to be orthogonal. So let me show you what I mean when we have a repeated eigenvalue. Okay, so it's true in general for, these observations are true in general for every symmetric matrix with real entries. We're now going to look at orthogonal matrices. Now, symmetric matrices and orthogonal matrices are going to be linked very closely in this lecture material. Okay, so what do we mean when we say an orthogonal matrix? Well, we mean the following. Suppose I've got a square matrix P, say with real components. We say that matrix is orthogonal if the inverse is equal to the transpose. Now, this is, you know, like when you see that, you should smile because in my experience, very few people really enjoy computing the inverses of matrices. Okay? But most people can quickly compute the transpose. So a matrix with property 3 is very nice because it saves you tons of work in computing the inverse. Okay? So this is a lovely, lovely situation to be at. Now, equivalently to this, we say the matrix P is orthogonal if its columns are orthogonal unit vectors. So basically, look at the columns. Do they have length 1? And are they all perpendicular to each other? If that's true, then we say the matrix is orthogonal. Okay, so in many cases, what we're going to want to do is diagonalize some sort of matrix, a symmetric matrix in many cases, and this is going to be just great to work with. Okay. Well, let me give you an example, actually, before we move on. Let me give you an example of an orthogonal matrix. Okay, so let's okay, this is an orthogonal matrix. If you look at the columns, say, they have length 1. And if you look at the dot product, between, say, this column and this column, it'll be 0. So that's a matrix that is orthogonal. And if you want to verify, so this is like, I don't know, let's just call the sort of U1 and U2. Okay, so U1 is like this vector, U2 is like this vector. Okay, it's pretty easy to see that. Now, if you want to, you can also verify that the P transpose equals P inverse in this case. Okay, so to compute the inverse of a 2 by 2 matrix is not that bad. It's not like calculating a 3 by 3 inverse matrix. Okay. Okay, so now what we're going to do is link these orthogonal matrices and the symmetric matrix ideas that we were talking about before. Okay, so suppose we have a symmetric matrix and we compute the eigenvectors. Now we know that for symmetric matrices, we can choose, the eigenvectors are either orthogonal or we can choose them to be orthogonal, right? So what we can do is form a new matrix, say R, by writing the eigenvectors of A as columns, okay? Now, that's almost a symmetric, an orthogonal matrix, but to make it orthogonal, what we do is we normalize. Make these eigenvectors have length 1. There'll still be eigenvectors, but if we write all those normalized eigenvectors as columns and form a matrix, then we will get an orthogonal matrix, P. Okay, so this is going to prove to be massively time-saving when we're solving other problems, because if we can put this matrix P together, we don't have to calculate P inverse, just P transpose, which is pretty easy to do. Okay? Now, this matrix P, based on this special form here, will diagonalize any real symmetric matrix A. Now, what do I mean when I say diagonalize? Well, I mean the following. P inverse AP equals a diagonal matrix with the eigenvalues down the main diagonal. Okay? So I've put in a little bit of a proof there, just to sort of verify it and show you. So if you look at A times P, it's just this times this. I can sort of multiply the matrix A with each column of this matrix here. And because all the lambdas are eigenvalues, I can go from here to here. Okay? So what I can do now is decompose that back to P times some diagonal matrix with the lambda 1, lambda 2 down the diagonal. So this is just P times the diagonal matrix. So if I take the inverse P of both sides, I'll get this P inverse AP equals the diagonal. Okay, and since P is orthogonal, P inverse is just P transpose. Okay, so diagonalizing a matrix is important because it simplifies the calculations involved. You start with a difficult system, you diagonalize the matrix involved, and you get a simple system that you can almost solve just by inspection. So that's the motivation. All right. So let's have a look at some sort of application of this, these symmetric matrices, these orthogonal matrices, and this diagonalization approach. So the principal axes theorem. The principal axes theorem is one of the main focuses of our study on matrices. Okay, so we're going to look at forms like these forms here, called quadratic or quadric forms, and simplify them using matrix methods. Okay, so just as some motivation, look at these functions here. What would the graphs of these functions look like, or what would the surfaces look like? Even for this one, it's still really hard. Just working in the xy plane here, right? It's really hard. What we're going to do is use these matrix methods to actually simplify these expressions a lot. Okay, so our interest will be in the following form. Okay, so just say a simple form like this in 2 dimensions. So here A, B, and C are just constants. And so if we go up to, say, 3 variables, all right? Now this is extremely complicated, as you can see. The A, B, C, D, E, and F are constants. Okay? All right, so it's not clear, for example, what the graphs of these functions will look like. What we're going to do is apply a change of variables, or a change of axes, that will greatly simplify the analysis. Now, the basic idea is that these quadratic forms of interest can be written using a symmetric matrix A. Okay, so for example, if we go use this Q up here, I can write this as some vector transposed times a symmetric matrix times a vector. Okay. So in this x is like this, or in this, I guess in this context it might be you've only got sort of 2 variables here. Okay. So let me sort of give you a bit of a flavour for the ideas first. Suppose I could diagonalise this matrix here. So I've only got things going down the diagonal and zeros everywhere else. And I had a new set of variables, not x and y, something else. This multiplication would give you something squared plus something else squared, okay, with some coefficients involved. That's a lot simpler than something like this. Okay. All right. So let me show you the connection with these orthogonal matrices. Suppose I have some quadratic form. Here A is a n by n square matrix that's symmetric. x1, x2, etc. are our variables. Now we know that we can find an orthogonal matrix that diagonalizes this A. Okay? Now, if we go up to 4 and replace A with P times D times P transpose, then we obtain the following. Okay? So, if we define a new set of variables, say y, via this substitution, then this previous line becomes, okay, well, let's replace x with py. Then I can use the transpose properties to simplify this. And if you look at what's in here, this whole thing, okay, p transpose p, that's p inverse p, that's just going to be the identity. P transpose p, that's going to be the identity. So in the middle, I just get the identity times d times I, which is just d. And I get this form. Okay? Now, it may not look that simple on the screen, but that bottom line is a simple form when you're working in, say, 2 or 3 dimensions. It's a far simpler form. Okay? Far simpler. In other words, what you can do then is maybe sketch the graph of this form in your new set of coordinates and then transfer it back to, say, your original coordinates. Okay, so essentially what I've just shown you is some justification for the so-called principal axes theorem. Okay? Now you don't need to remember this explicitly, but you do need to remember the basic idea behind it. Okay, so suppose I've got a real symmetric matrix and I compute the eigenvalues. And then I compute the corresponding eigenvectors. What you can do then is choose all these things to be orthogonal, make each of them have unit length, and then form this orthogonal matrix P. Okay, so let's say I do that. Well, if I make this change of variables, x equals py, then this potentially difficult quadratic form reduces to the so-called principal axes form. So essentially it's just a sum of squares involving the new set of variables and your eigenvalues. In addition, these normalized eigenvectors form a basis for whatever space we work in, r squared or r cubed, that lie on the principal axes. Okay, so if you sketch in, say, your eigenvectors and then sort of extend them as axes, they'll just form a new set of axes, principal axes. Okay. Okay, so this is a good example. There's a number of sub-questions there. Here we've got a quadratic form. By changing coordinates, write Q as the sum of squares. Okay, so the first thing we're going to do is write this in the following form, where x is just the following. Okay, so remember the vector x and the real value x are two different things here, so don't get confused. So I want to write Q in this form where A is a symmetric matrix. Okay, so how do I do it? Well, if I look closely, okay, I'm just going to squish it in here. For these functions of 2 variables, the following symmetric matrix can be put together. Well, look at the squared terms first. We've got 3x squared and 4y squared. To write that in this A symmetric matrix A form, just write those coefficients down the diagonal. Okay, so 3x squared and 4y squared gives you the diagonal components. The coefficients give you the diagonal. Okay, now there's one other term that's left over in here. It's 2 root 2. So what I do is I take half of that coefficient and write it in the remaining positions. Okay? So when I'm trying to write this quadratic form in terms of a symmetric matrix, A, I write down the diagonal first just by using the coefficients of the squareds, and then I look for what's left over, half those coefficients, and write them in the other places that are not on the diagonal. Okay, so the two variable case is the most simplest case here. All right. So I'm going to do these. Again, there's a fair bit of writing for this one, so you might want to draw a column or something here. Now note, is this a symmetric matrix? Well, yes it is. Okay, A is a symmetric matrix. Okay, so we like that, we're in a good spot. Now by the principal axes theorem, the PAT, I know that I can write my quadratic form as a sum of squares, where y1, y2 are the new set of variables, and the lambda 1, lambda 2 are the eigenvalues for my symmetric matrix A. Okay? So, let's look at the first part of the question. By changing coordinates, write Q as the sum of squares. So to do that, all we need to do is calculate lambda 1 and lambda 2 from A. So eigenvalues, lambda of A, satisfy the following. It's A minus lambda I, the determinant of that, equals 0. So I want to solve this and find the values of lambda that satisfy this equation. Okay, well, A minus lambda I, so I'm going to get 3 minus lambda and 4 minus lambda down the diagonal. Okay, and now I just want to expand this 2 by 2 determinant. I'll get some sort of quadratic, and so I'm just sort of continuing on from this line. I'll get the following. So it's this times this minus this times this. Okay, so I've got a quadratic. Hopefully it'll factorise neatly. If I expand this out, I'll get something like this. And then lo and behold, I can factorise this. Okay, so I think it's going to be something like lambda minus 5 and lambda minus 2. Okay, so my eigenvalues are going to be positive 5 and positive 2. So actually, that's all I need for the first part of the question. All right. So by the principal axes theorem, Q equals lambda 1. So let's make lambda 1 5 and lambda 2 2. Okay. It's pretty easy. Don't need the eigenvectors for that. All I really need is the eigenvalues. So I've written Q as the sum of squares there, just involving the principal axes theorem and these lambdas. Now it doesn't matter if you put the lambda in, the 2 here and the 5 here, if you switch them over, it's still correct. Okay, but I've just chosen it to do it this way. Well, they're okay, the y1 and the y2 are a new set of coordinates. Okay, so we don't need to calculate them or the eigenvectors or anything like that yet. Okay? Yet. Okay, so that's the first part taken care of. Write Q as the sum of squares. Sketch the level curve, Q equals 1, with both sets of axes on the same graph. So let's have a look at that. Okay, so what I'm going to do, set this equal to 1 and sketch it in the y1, y2 plane. Okay, so now I'm working the new set of coordinates. So what kind of curve will this be, this bottom line? What kind of curve? An ellipse. Okay? Now, it's not too hard to sketch this in the y1, y2 plane in the new set of coordinates. You should get something like this. So this is positive 1 on root 5, negative 1 on root 5, 1 on root 2, and minus 1 on root 2. Okay, I know it's a bit small, but you can derive. You can find out those intercepts pretty easily. Okay, so that is in our y1, y2 space, in our new set of coordinates. What we want to do now is somehow relate that coordinate system back to the xy plane. So we want to draw the ellipse in the xy plane. Now for this particular example, all that's really happening here is that the ellipse is just being rotated. You've got you've got your xy axes and they're just being rotated to form some sort of new ellipse. Okay? That's and you'll see that in a minute. Okay, well, how do I sketch these on the same set of axes? Well, what I need to do is go back and now compute the eigenvectors, because the principal axes theorem tells us that the eigenvectors will lie on the principal axes. Okay, and I can relate them back to the xy, the x and y axes. Okay, so I'm going to take a new page to do this. So I've got my eigenvalues. What I want to do now is separately compute the corresponding eigenvectors for lambda equals 5 and lambda equals 2. So this is sort of like, this is a continuation of what's going on here. So 2 continued. So let's just take, say, lambda equals 5. Then I want to solve the following. So it's going to be something like minus 2, minus 1, root 2 and root 2. So I want to solve this for V1 and V2. So if I expand out, what's going to happen is we're going to obtain the following. V2 equals root 2 times V1. Okay, so what I can do now is say choose V1 to be 1 and V2 will be root 2 then. Okay, so an eigenvector, let's call it, say, I'll just call it V1, would be 1 root 2. Now, even though that's an eigenvector, what we want to do is form some sort of orthogonal matrix with the columns as the eigenvectors. Now, this does not have length 1. Okay? So what we're going to do is, as a final step, we just need to normalize this vector. Okay? Okay, so the little hat means it's got unit length. The length let me just adjust that, root 3. Okay? All right. So that's the case lambda equals 5. Let's go back and look at the case lambda equals 2. So what we're going to do here, we're going to solve the following. We're going to get 1 and 2 down there, root 2 and root 2. Okay, so it's similar to the previous case, except we've just got v1 equals minus root 2 v1 equals minus root 2 v2. So let's say we choose, say, v2 equals 1. I'll get the following, and I want to normalize that. So, oops. So the length again is going to be root 3. So that's my eigenvector. Okay, so what we've actually done now is computed the axes in our new set of coordinate system. The v1 and the v2 will lie on the set of axes in our y1, y2 space. Okay, so what we're trying to do is sketch both sets of axes on the same graph. Well, I've got that thing to work with there. So let's see if we can sketch these things in the xy plane. All right, so all I really want to do is sketch that vector and that vector. Okay, so it's going to be something like, it's going to go up a bit more. Okay, and it's going to be something like that. Okay. Okay, well, how can I relate that back to my previous picture? I'll come back to this. Think of a vector going along this axis, v1, and along this axis, v2. So if I sketch in, say, my axes associated with these eigenvectors, and let's say I'm just going to draw in my ellipse. Okay, this is a pretty rough drawing, but hopefully you get the idea. Right, so look at the relationship now between this picture and this picture. You can see essentially the axes have just, you know, if I wanted to sketch in, like draw these axes here, this would be your y1 and this would be your y2. Okay, these axes have just been rotated around the origin. Okay, can you see that? Now the last part of the question was, what is the closest point on the curve q equals 1 to the origin? Okay, well, since it's just a rotation, you can kind of sort of see it from here, right? It's either going to be, this is in the y1, y2 coordinate system. It's either going to be that point, well, actually they're equal distance from the origin. So there's 2 points that are closest, that point and that point. Now in the xy plane, what do those 2 points refer to? Again, you can probably see them. It'll be that point and that point. Okay, so you know, maybe call that C and that point D. So the question is, how do I find those points? Well, with this one, it's you know, at least we know the line that it lies on. It's not always so straightforward. So what we're going to do is kind of use a little bit of matrix multiplication between the two. So, so this, I guess this is part 3 now. I'll just see if I can squeeze it in here. So in the y1, y2 plane, C and D. Okay, so, you know, say C and D or something like that are the closest. So the question is, how do we get the xy coordinates for these points C and D? Well, we use the following. Okay, so it's just essentially a matrix multiplication here. So say for the point C, well, in the in the y1, y2 plane, this will be the point 1 on root 5, comma 0. Okay, so the x coordinates is just the following. So it's, let me see if I can squeeze that in. 1 on root 3 times your matrix P times the coordinates in the y1, y2 plane. Okay, so what are we going to get here? Well, we're going to get something like 1 on root 3, 1 on root 5, root 2 on 5. Okay, you can clean it up a little bit if you want. And similarly, D is going to be, D is going to be similar. Okay, minus 1 on root. Okay, so that's just going to be the negative of that. Okay, so I've been a bit lazy there, and I probably could simplify that a bit more. Okay, a reasonably long question, but the only reason it was long is because there was lots of little subparts to it. Now, hopefully, you can see the advantage of using this principal axes theorem. You take something that's very complicated and essentially really understandable. You form a new set of coordinate systems through a substitution. You sketch the graph or whatever it is in that new system of coordinates and then relate it back to your original xy system. The point is that each of those little sub-questions in that exercise relies on something from this topic: eigenvalues, eigenvectors, symmetric matrices, orthogonal matrices, principal axes theorem. Okay? All right, so this is a slightly nicer one because it doesn't demand so much work. By changing coordinates, write Q as the sum of squares. Okay, so the first question is, can I write this as x transpose times the symmetric matrix times x? Okay, so what I would like to do is write it in the following form, where here I'm working with x, y, and z. Now, this is a bit of a challenge. I'll be working with a 3 by 3 matrix now. So how do I form a 3 by 3 symmetric matrix A to sort of take care of this Q. Firstly, there's no squared terms here. Okay, so there's no x squareds, y squareds, or z squareds in there, right? So the diagonal is just 0. Okay, so let's go to the first one, xy. Halve that coefficient, positive 2, halve it and put it there and there. Okay, now you'll see there's 0 xz in here. So I take half of those coefficients and write them here and here. Now, yz, the coefficient is positive 2, so take half of those and write them here. Okay? Now, there is a general algorithm that I'll give you at the end. Okay, so don't worry too much about that. But, I mean, you know, x and y, x and z, y and z. Half the coefficient in each case. All right, so what we want to do is calculate the eigenvalues of that matrix A, and then just write, using the principal axes theorem, just write down Q as the sum of squares in the new coordinate system. Okay, so this is a pretty reasonable example as long as you can compute the eigenvalues of this matrix. Okay, so I'm just going to get zeros down, minus lambdas down the diagonal. Okay, so now what I want to do is expand that. Now, as you know, I usually expand these across along the top row. We've got a 0 there. Okay, so that's going to simplify things. So actually, I'm going to get something like the following. This might look familiar to you. It's that times the determinant of that minus 1 times the determinant of the following plus 0 times the determinant of this. Okay, so actually this is the same determinant that we calculated in the previous lecture. So if I expand this out, I'll get the following. Okay, so if you want the details, they're in a previous example. So lambda equals 0, positive root 2 and minus root 2. Okay, so now we're actually at a good spot because we just need to write down one more line and we're finished, right? We just invoke the principal axes theorem and say the following. By the principal axes theorem, Q can just be written in the following form. Okay, so you've got a new set of variables, y1, y2, y3, and we can write Q as the sum of these squares. Now, it doesn't matter how you, squared. Sorry, not cubed. Is that what you're going to say? Yep. So, principal axes theorem tells us that I can write Q as a sum of squares, right? Now, it doesn't matter which way you put in your lambdas here. Okay, it's still going to be correct. So I'm just going to make lambda 3 equals 0. Okay. Okay, so how do we write a quadratic form involving x, y, and z as in a form involving a symmetric matrix? So I said in the earlier part of this lecture that I would give you a little algorithm at the end. So here it is. Okay, so A, B, C, D, E, and F are all constants. So how do I actually write this in the following form? For some symmetric matrix A? Well, it's just the following, okay? So you look at the squareds and you write the coefficients down the diagonal, right? So let's go to the xy. Here I've got b times xy, so I take half of that and write it here. So let's move on to the xz. The coefficient here is d, so I go to here and write down half of that coefficient. And lastly, yz, the coefficient's e here, so the last two entries will be half of the coefficient. E on 2 and E on 2. So that algorithm will work in general for these quadratic forms.